Hello, Algebra 2. Mr. Richardson coming at you live via Screen-O-Matic or Cast-O-Matic or something like that. Anyway, today's 5A, Unit 5A, Day 6, Learning Target. I can find inverses of tables and graphs and determine if they are a function. All right, so first of all, what's a function? We've been talking a lot about functions lately. We just maybe haven't defined it very well. So a function is when each x or input has one output. Okay, so the easiest way I can define that is just by a table. All your x's, you can have no repeats. Your y's can repeat all the time. So each x or input has one output. Okay, 0 has 5. Now they're the same outputs, but that's okay. What you can't have, what you can't have, and I'm going to use our new terminology. So that's our function. That means the same thing. Is we have two inputs going to the same output. We cannot have that. That's not a function. So graphically speaking is probably the easiest way to demonstrate it. Most of the graphs that we've talked about, all right, that would be a function. You have what's called the vertical line test. If you can draw a vertical line anywhere and it only intersects the graph once, then it's considered a function. So our quadratic, also a function, etc. What's not a function is something that may look like this. How about this? All right, see the vertical line test intersects it there and there. That's not a function, okay? Anything kind of breaks up is not a function either. So like a step graph, something like that. If there's breaks there, that's not a function. So you got an idea of kind of what a function is from a table and a graph. Okay. So this next part says work with a partner. You might be doing that in class, but for our video purposes, I'll graph some of these. I don't think I'll do all four, but I'll graph a few of these on our calculator and see what they're talking about. Maybe I should read it first. Each pair of functions are inverses of each other. What does that mean, inverses of each other? I know when I'm solving equations in Algebra 1, Geometry, or Algebra 2, the inverse operation is the operation that undoes the other one. So the inverse operation of multiplication is division, of squaring is square rooting, subtraction, addition, etc. Okay, so these are inverse graphs. Use a graphing calculator to graph f and g in the same viewing window. What do you notice? Well, let's check it out. No, I don't want that calculator. I want this one. Forget that one. All right, so get out of there. Causing all kinds of problems. Okay. So the first one is 4x plus 3. So 4x plus 3. And then I'm going to go down one and graph this other one. I do have to put the top in parentheses, I believe. I'm not totally sure there, but I'm going to do it just to be safe. Okay, so we're going to graph these. Hopefully my window is normal. Okay, so they are inverses of each other. They look like they're reflected somehow or a way. That's my first observation, but I think I'm going to have to do another pair to decide if that is true or not. So first of all, I'm going to get rid of those two equations, and I'm going to do the next two. All right, what are the next two? Which ones do we want to do? Oh boy. All right, let's try B. So this is x to the power of 3 plus 1. And then this other one's going to be a little harder, so I need the cube root of, okay. So I think I got to go to math. Okay, I need cube root, so I'm going to go 4. And then I'm going to put x minus 1 under there. So you can see kind of the cube, the inverse of this. This is cubing, this is cube rooting, adding 1, subtracting 1. Let's graph. Let's move over there a little. Oh my gosh, definitely a reflection. I wish I could annotate, but it looks like a reflection kind of right down this diagonal line here. I can't show you. How do I annotate? I can't annotate on this, I don't think. Anyway, to me, and again, it's going to be probably harder for you to see the first time, but it looks like a reflection over the line y equals x. And I remember that from geometry. So when I want to reflect from geometry, when I want to reflect over the line y equals x, I switch the coordinates. So maybe that'll apply here. All right, so I'm not going to bore you with the other graphs, but I think you could probably do those on your own, particularly D, use parentheses, and just see if that is true. So I'm going to write that down here. I think, what did I notice? I noticed that each function and its inverse were reflected over the line y equals x. And again, I think that's true because we learned that some of that in geometry. All right, let's do a live example. So let's create a table here. I'm going to use easy points here. I'm going to use that one. That one looks like 2, 4. I'm going to use that one and that one. So I'm going to put the 0, 0 in the middle. I'm going to put 1, 1 there, and I'm going to put 2, 4 there. I'm going to put negative 1, 1 there, and negative 2, 4 there. So those are my x's and my y's. Okay, and that's the blue graph. Okay, so let's create a new table. And again, from geometry, I know that if I want to reflect over the line y equals x, then I just switch the coordinates. All right, so I'm going to go 4, negative 2, 1, negative 1, 0, 0, flip to 0, 0. All right, and then 1, 1, flip to 1, 1, and 4, 2. Okay, we did that. So I think those are inverses because I think inverses for graph speaking reflect the graph over the line y equals x. So we're gonna have to remember this graph because they want us to do, I think on the next page we're actually graphing it. Let's graph it here, and then it doesn't fit very well here, but let's try our best just because it's all on the same page. So in blue, in blue, I'm gonna graph this new line. So 4, 2, so 1, 2, 3, 4, negative 2, I should say, is approximately right there. 1, negative 1 is there. 0, 0 is there. 1, 1 is still there, and then 4, 1, 2, 3, 4, 1, 2. So it's going to look like that. So it's kind of that parabola put on its side, but if you look at the line y equals x, almost perfect. So I think our observation is right. Inverses of each other are flipped, at least the graph speaking. The coordinates are just flipped, period. And let's write that down. Coordinates switched, let's say, not flipped, although it does cause a flip. Switched. So x and y becomes yx for the inverse. So function inverse. And I think it's true because the graph looks true there. So I think the first stuff on the next page was kind of graphing. We did that. It looked kind of like this, and like something like this, and we'll split there. I guess I should have used blue there. Okay. What do you notice about the two graphs? What is the domain and range? Whoa. So the green domain and range, the domain would have been negative infinity to positive infinity, meaning I could have used any x's, and they're eventually going to go, even though they look like they just kind of go up, they're eventually going to go left and right to infinity. So the range, a little different though, the range went from, 0 to positive infinity. So when we flip, for the red graph, when we flip it over the line y equals x and we make it go sideways, we also switch. So if we switched all the x's and all the y's, and that's what we did, that means the domain and range would be flipped kind of accordingly. So this domain then would be 0 to infinity, and the range now would be negative infinity to positive infinity. Let's see if that's right. So domain is a set of x's, so it starts here and goes that way. So yeah, that's just positive x's. And because these are kind of slanting up and down, it will eventually get to positive and negative. infinity. Find the inverse of the given table. So this should be easy. All right, so inverse xy. We just flip -7, -1, 9, 0, 10, 1, and -3, 2. Okay, and then we notice the domain of our original function, the domain was, we just list it, so -1, 0, 1, 2, and the range was, the y's, the outputs, -7, oh, it's not really in order, oh well, it's too late, 10 and -3. And then, you know, for our inverse function, it's just going to flip. So this is now -7, 9, 10, -3, and that's what it means to find the inverse. Kind of the flip. And then the range would be -1, 0, 1, 2. All right, so we're doing okay. Give the graph, draw the inverse. Is the inverse a function? Oh, okay, so the graph is a function. Look, I'm going to do the vertical line test. Bloop, 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 bloop. The graph is a function here, so yes, my graph is a function. They want to know if I graph the inverse, is it a function? So I guess there's a couple of ways to do this. We could just plot some points here. It looks like you got 0, 0, 2, 1, 5, 2, and 10, 3. So let's make this table here. So we got 1, 0, 2, 1, 5, 2, and 10, 3. So if we want a new graph over here, we just flip everything here. So we got 0, 1, 1, 2, 2, 5, and 3, 10. So 0, 1 is right there. 1, 2 is there. 1, 2, 1, 2, 3, 4, 5 is there. And then 3 and 10. So it looks something like that. And it looks like it may go on forever. That was going on forever. So that still looks like a function to me. That always isn't the case, as we saw with the quadratic. But this looks like a function to me. What is the domain and range? Okay. So the domain looks like it starts at 1 and goes to positive infinity. The range looks like it starts at 0 and goes to positive infinity. All right, which means that our domain and range for our other one would just flip. So domain is 0 to positive infinity. Yep. Domain, yeah, because we're starting 0 and going that way. And then the range starts at 1 and goes to positive infinity, which sounds about right because 1 is the smallest y value. All right. So hopefully, I know I go a little fast, but you got a lot of video here. A lot of stuff to go over, and the video lasts about 15 minutes. And I don't like to go over 15 minutes, even though I probably could. So I went about 13 minutes. So hopefully you do enough kind of practice in class and discussion with your teachers. You could pause this or rewind it and go over things twice. But thanks for sharing, and talk to you soon. Bye.